Hi, welcome to this lecture on data representation. So in this lecture, I'm focusing on how data is being represented in the computer. So what do we mean by data? Well, when we talk about data in a computing process, we often speak about the data that humans consider to be of particular importance. So for example, humans love to write things down, so we want to be able to represent text. We want to be able to represent numbers. We want to be able to represent audio. And what about images? And if we put some of these images together, we can have the experience of video. So these are all particular types of what we call multimedia. So these are types of multimedia that we want to be able to model in a computational process. So the title of this lecture is called Data Representation. All right. Oh, and if you don't know who I am, my name is Professor Ritesh Judah. Okay, so this is basically what we are really interested in, and it turns out that representing data in a computational process is quite an interesting task, because the way we represent this information directly impacts the speed of the retrieval of this information. So the way we represent our data influences something called runtime of our programs, and also this translates to different types of storage demands. And we'll see what this means in a few in a few minutes. So when we talk about storage demands, we often find that different types of multimedia, like text, for example, requires a different amount of storage, a different amount of cells of memory to be able to store something compared to, let's say, a number. Audio might require more storage than numbers, and images require a different quantity, and so on. And videos obviously require more than images. So we have this trade-off, right, between the storage demands and the runtime that our particular algorithms are going to be using. So what's quite amazing about computation is the fact that everything that makes a computer special, I've said this many times in the lecture, like this ability to represent text and numbers and audio, images and video, this all is done using the simple concept of binary. And a binary, as you know, is a, you can think of as a number system, which is the language that we use to represent these different things. So this language takes the form of a 0 and a 1. And we use this language inside of a constraint called a bit. So a bit is the expression that we can use. So we can have a bit with a 0 inside of it, or a bit with a 1 inside of it. And it's what these bits that we together are able to represent different things. So to be able to put this into perspective, let's have a look at a byte of memory. So a byte of memory is just, if you put 8 of these bits together, you get a byte. Okay, so here's an example of a byte of memory. Okay, so the big question then is, how much of things can we represent using this byte of memory? So how much of the piece of an image or a video or different numbers can we represent with just 1 byte of memory? So let's see. If I assign this particular string to represent, let's say, a cat, right? Then how many different things can I represent with 8 bytes, with 8 bits? So to calculate this, we use something called the fundamental counting principle. And here we say, okay, there's 2 options for this first bit, there's 2 options for the second bit, there's 2 options for the third bit, 2 options for the fourth bit, and so on and so on. Altogether, we get 2 to the power of 8 different options, which is 256. So this is how many different options we have to represent something using 8 bits. So what is that something? Well, maybe this is the symbol for cat, but then I've got another 255 different strings of zeros and ones that I can use to represent other things. Okay, so these bits, as you can imagine, are the units of computation. So So it's an interesting concept in and of itself, right? Because your units of distance can be kilometers, your units of mass can be kilograms, but the units of computation is bits and bytes. Very interesting. Okay, so let's look at these units of computation a bit more. So we're going to state the unit here. Okay, so we'll look at kilobytes. We'll call it KB. Okay, and then we have, oops, I'm using a writing tablet, so sorry if things look a bit weird. Okay, we'll look at the unit. We'll also look at the equivalent in bytes. Okay, and then we'll also look at the common uses. So this common uses is directly related to what we spoke about when we spoke about storage demands, right? This common uses, because this common uses tell us about what do these objects typically occupy in terms of these units of computation, in terms of these bits and bytes. So let's go back and actually see what these things are. So kilobyte is about 1024 bytes. Remember, a byte is 8 bits. Okay, this is more or less 2 to the power of 10 bytes. Okay, and we have kilobytes. When we use kilobytes, we often refer to text documents, things like this. So text documents and other kinds of similar things, like just a whole bunch of files that represent some characters or numbers or anything like that. So we refer to those. That is the typical unit for text documents, so kilobytes. Well, we have a bigger abstraction called megabytes. This is often referred to as MB. And here we have about 1024 kilobytes, or approximately 2 to the power of 20 bytes. Okay, so when we talk about megabytes, we often talk about images. So these we usually describe using megabytes and short videos. Okay, then there's also gigabytes. I think these are concepts that you've seen before. Gigabytes, and then we have a G and a B. So this would be about 1024 megabytes, or approximately 2 to the power of 30 bytes. So when we talk about gigabytes, we sometimes talk about software, like operating systems or Microsoft Word suite, or there's lots of other ones, and longer videos. Okay, and then we have another abstraction which has more bytes inside of it, and this is called a terabyte. So this is similar to how you would get grams and kilograms and the rest of them. That you have these collection of grams give you a kilogram and so on. So this is the same kind of concept. So now we're talking about terabytes. So when we talk about terabytes, we have 1024 gigabytes, approximately 2 to the power of 40 bytes. Okay, I hope this makes sense. So when we are talking about terabytes, we often talk about data sets. I'm sure you must have noticed on Google Photos, for example, sometimes you need terabytes of information to store things, not necessarily gigabytes, and you pay for that for all of your many photo collections that you have. So this is now also file collections, like for example Google Photos. Okay, so we also have the last two is petabytes, also called PB, and we have exabytes. And this one has about 250 bytes and 260 bytes respectively. Okay, and when we talk about petabytes and exabytes, well, here, this is now the most significant collections. These are data centers. global internet traffic, etc. Right? So you can think of many more examples. So this is an interesting diagram because it really shows us that there is quite a lot going on when we talk about these units of computation. We're actually describing objects themselves. Okay. So let's move on. So then let's go back to this concept about data representation in itself. So we spoke about the concept of a bit and a byte, but we can also talk about how many objects can be stored with other descriptions of bits. So for example, we have 3 bits, right? So here we got 3 bits that are sitting next to each other. How many things can this represent? Well, here we would have 2 multiplied by 2 multiplied by 2. Right, so this would be 8, or 2 to the power of 3. So here you can represent 8 things. So what are these 8 things? So the 8 things it'll be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are 8 things. If you count them up, 1, 2, 3, 4, 5, 6, 7, 8. These are 8 things that you can represent. Okay. And if I have these 8 things, I can actually represent them. I can assign different things to it. So this can be apples. This can be a grape. This can be bananas. Okay, this can be oranges. This can be kiwis, a pear, a watermelon, and finally a nachi. Okay, so here we now have different fruits, all assigned a 3-bit binary string. So if I wanted to represent another fruit that's not here, I won't be able to. It doesn't exist in the language, right? So, for example, I don't know what's not here. We've got pears, we've got apples and grapes, blueberries, right? So suppose we want to represent a blueberry. Well, you can't, because there's no such a thing as a blueberry in this representation. We would need to then have 4 bits to represent the blueberry. Okay, so the 4th bit will be something like this, 1, 0, 0, 0, and this can now be blueberries. Okay, but for that to happen, I would need to add a 4th bit to each of these. Okay, so my point here is that if something isn't declared within the representation, it does not exist. So in this case, with 3 bits, there was no blueberries. Right, so this brings us to the concept of different types of memory. And when we talk about memory in modern computing, we often talk about 64-bit machines and 32-bit machines. So we have 32-bit machines and we have 64-bit machines. So let's talk about the 32-bit machines first. So a 32-bit machine is organized into 32 bits. So that means that each, so here we had 3 bits. Now can you imagine 32 bits next to each other? Okay, so there's 32 bits. And these 32 bits represent something. And it can be anything, right? So at this point in the course, we can think of a 32-bit word as being a whole lot of bits stuck together in one long string. In reality, this isn't the case really, right? In reality, memory is organized into bytes. So for example, in reality, this would be what memory looks like. So this is the first address where you have 1 byte of information. The second address has another byte of information. The third address has another byte of information. The 4th address has another byte of information, and so on. And this is basically how it works in the real world. But for the sake of just introducing these 32-bit machines and 64-bit machines to you, let's assume that this is how it's actually organized. And this is a word of memory. So obviously in reality that would mean that it'll be 8 plus 8 plus 8 plus 8, which is 32, and then this would be one word. So the computer will process this chunk of memory at a time. So more on this on this lecture on software, right? So we're going to come to this concept. But right now, what I want you to know about 32-bit machines is that a 32-bit machine allows for 2 to the power of 32 unique addresses. Okay, which is roughly about 4 gigabytes of information. Which is doable, right? It's about roughly 4 gigabytes of information that you can actually store. Well, if that's the case, and you've also heard of 64-bit machines, right? Then tell me. Okay, this is a recording, so you can't tell me anything. But you can just think for yourself. How many unique addresses will be referenced by 64-bit machines? Well, that'll be 2 to the power of 64. But you'll find out if you put 2 to the power of 64 in your calculator, that's an exorbitant amount of memory to represent 64 bits. So in practice, we don't really use, although in 64-bit machines, a word is 64 bits put together and information is processed in 64 bits at a time. In reality, the memory itself doesn't actually have an exhaustive list of 2 to the power of 64 different addressable locations, because it's impractical to do that, and space is actually quite expensive. So in reality, we just use about 40 bits to represent memory, and maybe about 52 bits, 52 but physical addresses. Okay, so that's an interesting concept in and of itself. Okay, so then let's look at the next topic. And this topic now is focused on representing numbers. So here we were representing grapes and apples and all different types of fruits in this example. Okay, and here we were talking about how we can use the space in memory to represent different types of objects. But let's now actually talk about representing the objects themselves. So, and we're going to do this for all of them. We're going to do this for text. Before we said we were going to do this for text information, for numbers, for audio, for images, and for video. We're going to do it for all of them, but we need to start somewhere. So let's start with numbers. So we're going to start with numbers. So this is representing numbers. So representing numbers is a very interesting thing in computation. And one way we can represent numbers is by simply just assigning every string of bits to a number, right? So suppose we've got 3 bits to represent numbers. So that's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Here we can represent maybe the number 0. We'll represent this with 1. This one will be representing 2. This one will represent 3. This one will represent 4. This will represent 5, 6, and 7. Okay, so we've got, with 3 bits, we can represent 8 things, and those will be the numbers from 0 to 7. So that's really nice. That's great. That's exactly what we want to do, and that's exactly what we've learned so far about representing things. So this is a good idea, but in reality, we also have to represent negative numbers too. So what about negative numbers? Okay, so what about negative numbers? Well, negative numbers is a very important concept. We need to be able to represent them. So how do we do it? And it turns out that in base 10, when we want to represent something negative, we would just sometimes add this negative sign and then put the number there. So it could be -5, -3, -10, -101, or whatever. However, in a computer, this symbol does not exist. We've got to use only the language of zeros and ones to be able to represent things. So similar to this concept is the use of ones complement. So let's actually look at what ones complement is. So for a binary number, b, which is equal to bn minus 1, bn minus 2. So these are the digits of the binary number, all the way to b1, b0. It's ones complement. It's 1 complement b prime is obtained by inverting each bit all right. So this is now the notation for the inversion. So we're inverting each bit. So we'll have to now invert each of the bits. So this is the first one, this is the second one, all the way to the third to last, and it's actually the fourth to last. Okay, so we'll invert each of them. Okay, let's complete the definition where bi bar denotes the bitwise NOT operation of bi. Okay, so this is simple to understand. So this just means that this is 1's complement. So this is 1's complement. All this means is that we are just flipping the bits of a number. So what does this b bar actually mean? It means that if you have, for an example, flipping the bits, if you have b is equal to 1 0 1 1 0, then b bar is going to be 0 1 0 0 0 1. Notice that when there was a 1, it became a 0, and when there was a 0, it became a 1. So for example, this 1 became a 0. Okay, this 0 here became a 1. This 1 here became a 0. This 1 here became a 0. The next one also became a 0. And then the final 0 became a 1. Okay, so in other words, we just flipped the bits. So this is the concept known as flipping the bits. It's called flipping the bits. I don't know if that's an inappropriate thing to be calling it, but anyways. Okay, so let's look at an example of 1's complement. Okay, so let's say represent -5 in base 10 using 1's complement in base 2. Okay, usually when we talk about 1's complement, we are talking about base 2. So we can say this becomes then, well, then what is 5? Okay, I have to also say using 8 bits. Okay, so how do we represent 5 with 8 bits? So b is equal to 1 2 3 4 1 2 3 4. So this is now 8 bits together to represent the number 5. So to get the complement of this, it becomes b bar, which is equal to now 1 2 3 4 1 2 3 4. Okay, so this is now the representation of 5, and this is the representation of -5. Okay, so this sounds really great. It sounds like we really have a way to represent different numbers using positive numbers and negative numbers, and this sounds like we've solved the problem of number representations. Okay, let's see if we've let's try to assess what's actually going on here with 1's complement. So with 1's complement, so when we talk about 1's complement, right, what is actually going on here? So let's do this in 3 bits. Okay, so if you have 3 bits, okay, this represents the number 0. Okay, if I flip the bits of this, okay, let me write it here. Okay, I'm going to do this without making it messy. Let's do it here. So 0 0 0 0 0 1 0 1 0 0 1 1. Okay, so I'm just writing out the different configurations of zeros and ones with 3 bits, and now let's actually label these based on what they could be, or what they are, not what they could be. So this 0 0 0 is a 0, okay, which means that this here is -0. Okay, this is a 1, okay, which means that this is -1. This here is a what is this? It's a 2. Okay, if that's a 2, then where's the -2? Okay, this one is -2. Okay, this is 3. So that means that this would have to be -3. Okay, so here we can clearly see, what's going on. We can see that this -0 corresponds to flipping the bits on this side. This -1 corresponds to flipping the bits of that 1. This -2 corresponds to flipping the bits of that 2. So when you do something like this, it actually really helps you understanding, because now we can see exactly what's going on. Remember, it's a finite domain, it's a finite space. So we can actually look at all of the possible configurations. Okay, so this is the first thing we notice here. Something that's really weird is that we've got two representations for 0. This is weird. We have a -0 and we've got a +0. This is our +0 and this is our -0. That's extremely weird. Having two zeros is unnecessary. So even though it's just one bit, it's really unusual. Let's also look at a different thing that's weird. So if I want to add two numbers together, let's look at an example of adding two numbers together using 1's complement, right? So I'm going to change the color to black and say, let's have an example. And this is the one I've done in the class. So A is equal to 0, 1, 1, 0, 1, 1, 0, 1. Okay, and this corresponds to the number 109, okay, in base 10. And then here's another number. This number is 110101110, and this corresponds to the number -41 in base 10. Okay, let's say now I want to add these numbers together. I've got a positive representation. I've got a positive representation of a number, and there's also a representation of the number which represents a negative number, which is -41. And if I add these up, it's actually doing a subtraction. So that's one of the beauties of that's one of the things we really want, a mechanism we want, because if we can do subtraction by doing addition, then we'll never need we won't ever need a special operation for subtraction. We can do all addition using an addition and all subtraction doing addition as well, just representing it using a negative number. So for example, if I say A plus B, I'm actually saying 109 minus 41, okay, which is 68. Okay, so I'm expecting to get 68 here if I have to add these two things together, because there's a plus over there. So let's actually see what will happen. I want to get a 68. Okay, so how do we do addition? Well, from the number systems lectures, you remember how to do addition. So it was 0, 1, 1, 0, 1, 1, 0, 1, and we add, that's our A. Let's add the B to it, 0, 1, 0, 1, 1, 0. Okay, so let's now add these two guys together and see what happens. So this becomes, I'll use a different color pen just so it helps when looking at it. Okay, so this becomes a 1, this becomes a 1, this becomes 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 0. This 1 here, I would like to write it down here, but I can't. I can't because in this particular representation, I have only 8 bits. So I can't write a 9th bit here. I can't, right? It's against the rules. The representation only allows for writing 8 bits. So first of all, we need to check if this is the right answer. Is this the right answer? Well, it's not, right? If I convert this number back to base 10 using PNP, I'm not going to get 68. I'm going to get 67, which means that this 1 was pretty important and I've lost it. I've got to add that 1 back in order to get 68. So what I do is I add the 1 back in. And when I add the 1 back in, I now get 0, 1, 0, 0, 0, 1, 0, 0. And this is now 68. Okay, so this special case of addition, when you have a carry from the most significant bit, which is this over here, I have a carry from the most significant bit. I've got to do this extra work. This extra work, we need to formally define it so that we can remember what's going on here for future cases when there is something similar. Okay, and this is called the end around carry. So let's define the end around carry, and we'll always remember to do it when there is a carry out of the most significant bit. So for any two n-bit ones complement numbers a and b, let s be their sum and c be any carry from the most significant bit. Okay, that's the leftmost bit of S. Then the final sum, which is we'll denote as R, with and around and around carry is R, which is equal to S plus C, where C is added as a regular binary digit. So this definition is called the end around carry. And we're going to see this again later on in the next lecture. Okay, so that's really nice. So there's big problems. I'm going to write the problems in red. Okay, so one's complement has big problems. Number one, 2 zeros. Okay, which is weird. And then the second thing is addition is not natural. Too much work. I don't know if you remember the very first lecture, Pravesh, Dr. Ranchot was saying that the best kind of computer scientists are the ones who are lazy, right? Because your objective should be to do the least amount of work. Because by doing the least amount of work, you are actually reducing your time and your space. The amount of space you're using and the amount of time that you're using to do it. So that's our target as a computer scientist. It's our target to always minimize these two constraints. And right here, we're not, right? We're wasting space. It's not an elegant solution, all right? We got 2 zeros, and thus we're wasting time. This is the time. We'll be taking more time with addition because now we've got to worry about carryovers. And you have separate circuits that do carryovers. And that's just ridiculous, too much of work. So this is not really how we do it in practice, representing numbers. But I have to show you this in order so you can understand the next concept, which is called 2's complement. And this is, 2's complement is how we actually do all of these really cool things. So this is called, the cool thing of storing numbers inside of a machine. So 2's complement. So what is 2's complement? Well, 2's complement is slightly different from 1's complement. And even though it's slightly different, it offers a really elegant solution to representing both negative and positive numbers. So before I actually show you what 2's complement is, let's look at a few number lines of 2's complement. So we're going to look at number lines as decimal numbers. Okay, so we'll look at a decimal number. So let's do something like this. Okay, so we're going to start off at 0. And the decimal number will be 0. And then on this side of the number line, we'll have the binary number. It's useful to think of things in this way, because if you think of it in this way as a number line, then you have a natural representation, right? A natural representation. I can't get this line straight. Let me just try again. There we go. Okay. So 0, and let's say this has 3 bits. And we'll do the other case of 4 bits now in a few minutes. I just want to show you, try to get this across, right? So, and show you how it's different from other ones. Okay, so here we've got 0, and it's going to be 0, 0, 0. Okay, and then 1, just as before, 0, 0, 1. 2 will be 0, 1, 0. So far, this is really normal, okay? But now negative 1 is going to be 1, 1, 1. Negative 2 is going to be 1, 1, 0. Negative 3 is going to be 1, 0, 1. And negative 4 is going to be 1, 0, 0. So this looks very similar to 1's complement, except we're just off by 1, right? So can you see the difference, right? So if I have to, I wonder if I can cut and paste. I can't really cut and paste it. But do you see that here our 111 was used for -0, and here our 111 is used for -1. Okay, so it's slightly different. There is a difference in the way this is represented. But oh, let's look at a different example. Okay, so let's look at this in using 4 bits. Okay, so now we've got the decimal number and we've got the binary number. Okay, and the decimal number and the binary number, and let's get the number line sorted. So there's going to be 16 here, right? So I'm just going to have to count 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so let's count to 8 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. So that'll be my 0, 1, 2, 3, 4, 5, 6, 7. So with 4 bits, 7 is going to be 0, 1, 1, 1. This is going to be 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, then 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, then you have -1, -2, -3, -4, -5, -6, -7, and -8. Notice that there's an equal number. There's 8 of these positive numbers, including 0, and there are 8 negative numbers. So 8 positive numbers and 8 negative numbers. And let's continue here. So this -1 will be 1, 1, 1, 1, just like before. Okay, it's going to be 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, then 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0. Okay, so basically you start counting, you go up, so 0, 0, 1, 2, 3, 4, 5, 6, 7, and then 8 becomes here at the bottom, 8, 9, 10, 11, 12, 1, 2, 3. Okay, wonderful. So that's really great. And now we don't have 2 zeros, right? We have 1 0, and everything else looks like we've assigned a binary string with 4 bits to every number in decimal. Not all of the numbers, but all of the numbers that are available to represent in this 4-bit way. And so the basic idea, let's talk about this actual conversion. The basic idea of 2's complement is to subtract the number of bits, the total number of things. So I'll write it down, to subtract the total number of objects that you can represent. Oh, you again. That you can represent using n bits from a number to get the complement. Okay, so that's the basic idea. I'm gonna write your basic idea. Okay, so for example, right, if we have a number, we want to represent the number -3. So let me say example. You want to represent the number -3 using 4 bits. So this -3 is in decimal. Okay, then how do you do it? Well, all you've got to do is say, well, how many things can be represented in 4 bits? So that's going to be, well, if here you have 1, 2, 3, 4 bits, right, then it'll be 2 to the power of 4 different things, right? So there's 16 things you can represent in 4 bits, just as we did here. Okay, the binary number for 16 is 1 with 4 zeros, 1, 2, 3, 4. So if we just subtract our number 3 which is 0, 0, 1, 1, from this number, then we will get the negative counterpoint, right? So the negative counterpart. So here we've got the 3 that we're interested in getting the negative of. And so we would expect when we do that subtraction, we should get this. So let's see if that is the case, right? So you're going to get a 2 here, 2 here, 2 here, and a 2. That becomes a 1. This is a 0. That's a 1, and that's a 1. So I'm expecting to see 1, 1, 0, 1. And indeed, this here, okay, corresponds to that there. Okay, that's wonderful. So that's great. So it works. Okay, try to get the pen back. Okay, it works. So this here is the same as this here. It works. So I can get any of the negative numbers in this way. So subtracting it from, well, it turns out that when we're doing this subtraction with the total number of things to represent using n bits, and then the total number of things to represent using n bits, and the actual number to get the complement of, what we're actually doing is we're doing an operation like this. Let me try to write it down. It's going to be with 8 bits. Let's say we have 8 bits, so it's going to be 1 with 8 zeros. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so that's in base 2, and we're subtracting it from our x in base 2. In this case, the example I gave you previously, that was actually negative 3, right? It was 3, not negative 3. So x was 3. So let me go back to the previous one. Right here at the bottom, there was a negative 3. So we needed to find out the 2's complement of 3 in order to get negative 3. Okay, so 2's complement to get negative 3. And we're gonna see now that there's a shortcut of actually getting it, as opposed to just subtracting it from the total number of things in the representation. So this number here can be broken up. We can break it up into 8 ones, and then we can add the extra 1 to make it this number. Okay, so we can break it up in that way. So we can first subtract this x from these 8 ones, and then just add the 1 after that. Okay, and it turns out that it looks like a very easy thing to do. It seems like a more complicated thing to do, but it turns out that it makes the process a lot easier. So let me rewrite what I just said. So this is equals to 1, 2, 3, 4, 5, 6, 7, 8 ones, okay, in base 2. Then we subtract our x in base 2, and then we add 1 in base 2. Okay, well, you're adding 1, but it's actually going to be 1 with 8 bits. All of these things are in 8 bits. So this is in 8 bits. This is in 8 bits, and this is in 8 bits. And the reason why this is a very easy process is because this operation here is nothing more than flipping the bits. So this is flipping the bits of x, which is a very easy process. So you flip the bits and then you just add 1. So then let's define this a bit more in a concrete way. So I'm sure you noticed in this course we talk about stuff, but then we mathematically define it, right? That's pretty important. And you'll see this in all of your other computer science courses. So 2's complement, given a binary number b, which is equal to b and minus 1 and minus 2 all the way to b3, b1, b2, b1, b0. The 2's complement b dash dash of b is defined as, so we got b dash dash is equal to b dash plus 1, okay, which is equal to, so we're going to now say bn minus 1, the complement of that, bn minus 2, the complement of that, all the way to b1, complement of that, b0, the complement of that, right? This is all in base 2, and you're going to add 1 to that. Okay, so where bi represents the bitwise NOT operation. Okay, wonderful. So this is really great. We've got a definition, and we now can do an example. So find the 2's complement of 5. Okay, so what is 5? Well, 5 is, we're using 8 bits. So using 8 bits, so 5 will be 0, 0, 0, 0, 0, 1, 0, 1. Okay, so what do? We flip the bits and add 1. So we are flipping the bits and adding 1. Flipping the bits and adding 1. Flipping the bits and adding 1. Okay, so let's flip the bits. We're going to get, what's the notation? So to get the b's complement, 2's complement, it's equal to flip the bits and then add 1. So we're going to, let's flip them. 1, 2, 3, 4. 1, 2, 3, 4. Right, flip the bits, add 1, which becomes 1, 2, 3, 4. 1, 2, 3, 4. That's the answer. So this is how we represent -5 in 2's complement as a base 2 number. So yeah, that's how we do it, and that's basically it. Okay, we can also generalize this. We can generalize this idea by looking at b's complement. Okay, if you're prepared for that. So we can generalize this idea for b's complement. Instead of 2's complement, we have now an arbitrary number based b's complement. For example, what is 3's complement? And 3's complement is, find the 3's. Let's say we're going to represent an example. Represent 0, 2, 1, 1, 2 in base 3 in using a 5-digit representation. Okay, so we want to represent the b's complement of this number. So to do that, we're going to say, well, b is equal to 0, 2, 1, 1, 2 in base 3. To get the b's complement, of this, you would have to subtract from this the total number of things you can represent in base 3 with 5 digits. And how much is that? Well, with 5 digits, you'll have 3 things here, 3 things there, 3 things there, 3 things there, 3 things there. Oh, that's too many. There's supposed to only be 5. So 3 and then 1 more there. Okay, so 1, 2, 3, 4, 5, right? So not this one. Okay, which means that you're actually subtracting this number from this number to get the b's complement. So this is equal to 1, 2, 3, 4, 5 minus 0, 2, 1, 1, 2. This is the base 3 number, it's a base 3 number, and if you compute this, you get the b's complement of it. So I think as an exercise, do the subtraction, and you'll get the number, and then you'll be able to know how to do the b's complement. Yeah, so this is very much the same as what we've done before in the number systems lectures. Number systems. This is the subtraction that I'm talking about. Right, so that's it. That's all you need to know about representing negative numbers. Yeah, we spoke about particularly representing integers and representing negative integers, but we haven't really spoke about, just as before in the number systems lecture, we left the real numbers for last. Okay, so now we're going to actually talk about how do we represent real numbers. How do you represent real numbers? Well, it turns out that we use something called floating point. So floating point representation. Okay, so we use floating point numbers to represent real numbers inside of a computer. And we don't use 2's complement. So we don't use 2's complement for this. So what is floating point? What is it, right? So, I mean, you've seen it before, actually, floating point representation. You just don't know that it's called floating point representation. And this floating point really comes from the fact that the radix can be moved around in a real number by multiplying it by the base that you're in. So, for example, here you can have the number 5.126, and this is equal to, it's equivalent to 5126 if I multiply 10 to the power of negative 3. Okay, so this part here is called the mantissa. Okay, here's the exponent and here's the base. All right. And you can do this because this number is in base 10, and the proof of this comes from the PNP formula, which I don't want to get into now, but you can just in your mind think about how does it relate to the PNP formula. Okay, it's all about manipulating the radix points by moving it around using exponents. Okay, so there's certain things that we need to understand about this equation. So it's always good to have an example, a practical example in front of us. So I think for all of the rest of this discussion, try to remember what's going on here. Okay, so I'll leave it at the top there so you can keep relating it, right? So notice that there's a sign here too, okay? There's a sign, it could be negative or positive. So that's also an important part of it. So we've got a sign, okay? I'm going to write it down here. We've got a sign, okay? We've got something called the mantissa. We've got something called a base. And we've got something called an exponent. I'm sure you know what these words mean. Maybe you don't know what mantissa means, okay? But now you know. And so, number one, let's talk about the sign. So you need a single bit. So our task here is to represent this number using a computer. And I told you already that computers use binary. So we need a way to represent the sign. Well, there's only two objects that the sign could take. It could be negative or positive. So it makes sense to just use one bit to represent the particular sign associated with the number. Okay, so we're going to say 0 is positive, and we're going to have 1 is negative. Okay, number two, we have to talk about that exponent. So how can we represent that exponent? So let's actually see. So the exponent is stored in something called biased form. Okay, this biased form just means that we've added a number to it. Okay, and why? Why do we have to add a number to it? Well, it turns out that at the time when we were creating these circuits to represent the exponent, it turns out that adding a bias to it, depending on if we had a single precision or double precision, which is a 32-bit machine or a 64-bit machine, adding that bias term, which was usually 127 for a 32-bit machine, made the subtraction a lot easier, made the representation easy. So the representation of this exponent, right? So and that's really the reason why. I mean, historical reasons. And you'll find that with a lot of the stuff that we talk about when we talk about data representation, sometimes just because of backwards compatibility, we keep these old habits of doing these things in this particular way. So for example, in ASCII, when we talk about it later on, you'll find that the first 32 things in the ASCII table, which I'll show you, is useless. It's useless today because we don't have the technology that they had at the time when they were using that table for a particular purpose. But because now all computers use it, we have to be able to make our computers backwards compatible, and so we keep all of these old habits. So even though you might think, now what is the purpose of this exponent? I mean, surely we can build of using this bias form, surely we can build circuits that can remove this, the addition of this number. Well, we can, but if we do, then we're basically changing the representation, and we now not making it standardized anymore. And there's no way to change everybody's computers. You can only change what you can. So that's why, and you'll see this all the time. We're going to be talking about this as a recurring topic of backwards compatibility and standardization. Right, so long story short, for the exponent, we need to actually add a number to it or subtract a number from it, and that number is something specific, which I'll give you. And the reason for that has to do with historical reasons and also hardware design. Okay, and this hardware design comment will make more sense when we talk about gates and circuits, which is a topic for another day. Right, the last thing that we need to talk about is this mantissa, because we spoke about bases like a lot, so there's nothing to talk about there. But the mantissa, we store in normalized form. So the mantissa, and I'll tell you what that is now. Mantissa is stored in normalized form. Okay, so for example, this number here, which is 5.126, we'll store it as 1.5126. Okay. And if we do that, then we only really have to store what's on the side of the radix point, right? We don't have to store this. This is called an implicit leading bit. It's implicit because we don't ever store it. We just assume that it's there. And it makes sense that it's there because it'll always be there. Unless the number is a 0, if there is something on the right of the radix point when we represent it, then chances are that it's not a 0, it's a 1. So we don't ever have to store it. Okay, so this sounds really like a lot of information, and I'm just going to add a little bit more information to it because I didn't tell you about what that bias term is or anything like that. So right now I need to talk about a few more things, but I'll try to structure it in a way that is useful to you, right? So first of all, we represent real numbers in a different way depending on whether we are dealing with a 32-bit machine or a 64-bit machine. And with 32-bit machines, we call these single precision. Okay, and with 64-bit machines, we have what we call double precision. I hope your notes looks better than my notes. I was never really known for making good notes, but I know you will make much better notes than me. I've seen some of your notes in class, and I'm sure you have colors and highlighters and a whole lot of really cool stuff. I mean, I'm just trying to get this writing tablet to put my ideas down. Whereas you actually have the opportunity to write this on paper. So I hope you are writing it on paper. And not just taking pictures of the screen, because I don't think that's going to help you. Although education is a funny thing. Sometimes certain things work for certain people. Okay, so the memory usage here, depending on if it's a 64-bit or a 32-bit machine, single precision or double precision. For single precision, we use 32 bits in total to represent the real number. In 64-bit machines, as you guessed, we use 64 bits to represent the real number. All right, so the real number here is with 64 bits and 32 bits, and that's just how it is. Okay, so the sign itself is represented with 1 bit. Okay, so it indicates whether it's positive or negative. All right, and the same thing here for the double precision. We also just need 1 bit for the sign or negative. Okay, then we have the exponent. Okay, now the exponent for a 32-bit machine it uses 8 bits for the exponent. Okay, and the bias, the one we're going to either add or subtract from the exponent in a 32-bit machine, is always 127. And in a 64-bit machine, we have 11 bits for the exponent. Okay, and the bias is 1023. Okay, these numbers look familiar. Finally, we look at the mantissa. The mantissa is remember the number, this part of the number. Okay, so this part of the number, whatever it is, it could be anything. This is different from the example from before, but it could be anything. Whatever this number is, that's the mantissa. So this comprises of 23 bits in a 32-bit machine. Okay, and in a 64-bit machine, it's 52 bits. And that's it. That's all you need to know. Yeah, so that's all you need to know. But what's the use of all of this information if you don't know how to apply it, right? So let's now actually look at an example. So let's look at an example. So suppose that we wanted to calculate. Suppose that we want to calculate the decimal value of the 32-bit floating point number. Oh my goodness, we're gonna have to write this down. So it's 0 1 0 0 0 0 0 1. Okay, 0 1 0 1. Okay, 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. And then 1 2 3 4. Okay, this is 32 bits. I hope it's 32 bits. Okay, I have to count them up. And so this looks really intimidating, but if you remember what I just wrote in that table, each of these, we can segment this to mean different things. So let's start segmenting. This very first one here is our sign. This very first bit is our sign. Okay, then what's the next? The next 8 bits is the exponent. It's 4, 8. Okay, and then the next 32 bits is the mantissa. Okay, that's your mantissa. So then let's actually do that. So let's write it down. So this is our sign. This is our exponent. Okay, 8 bits. Okay, this is 1 bit. This here is our mantissa, which is 23 bits. Okay, so far so good. All right, so let's interpret now what are we seeing here. So let's start off with the sign. So the sign is positive. It's a positive number. All right, which is great. So that's the first clue. It's a positive number. So that's what the sign says. Because it's a 0, it's a positive number. Okay, now let's look at the exponent. Well, the exponent is this part here. Okay, now let me write it down. 5 zeros, 1 2 3 4 5 and a 1 0. So that's 4 numbers in total. And this is, if I have to convert this to base 10 using the PNP formula, it becomes 2 to the 7 plus 2 to the 1, which is in my calculator, 130. Right, perfect. Okay, and then I said that in that table, remember I said you've got to subtract the bias. Okay, so we subtract the bias from this number, so it becomes 130 minus 127, which is equal to 3. So 3 is the exponent. So 3 is the exponent for this particular example. The third thing that we need to look at is the mantissa. Oh goodness, the mantissa is really long. It's this whole thing here. So that's one. How many zeros is that? There's 23 bits. So that's 1, 4, 8, 12, 16, 20. Okay, so 1, 2, 12, 16, 20. Okay, there's 1, 2, 3, 4, 5 groups of 4. Okay, so it's gonna be the mantissa is gonna be 1, 0, 1. And then there's 5 groups of 4. So it's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, but remember that the mantissa is actually in normalized form. So that means that there's a 1 here and there's a dot here. There's the implicit leading bit, which means that I can now ignore all of these zeros because they don't hold any useful information. They're all 0. Okay, so right. So that's really helpful because I can now calculate the final thing. It's going to be a positive sign. The sign is positive. I've got the implicit leading bit, which is 1, then 101, and then you've got, this is in base 2. You multiply that by 2 to the power of 3, which is equal to, I'll keep the plus sign, 1 plus, right, because that 1 is over here. So it becomes 1 plus, I've got to convert this now to base 10 using the GPNP. So everything you learned was useful, right? 1 multiplied by 2 to the power of minus 1 plus 0 multiplied by 2 to the power of minus 2 plus 1 multiplied by 2 to the power of minus 3, okay, and then also multiplied by 2 to the power of 3. Why 2 to the power of 3? It's because my exponent was 3, so this 3 comes here. And the base is 2, not 10, so because we are in binary. Okay. So that's where that comes from, and then this is equals to plus 1 plus 0.5, which comes from there, plus 0.125, which comes from there, okay, multiplied by 2 to the power of 3, which is equal to plus 1.625 multiplied by 2 to the power of 3. Okay, so this is a weird example because if I multiply this number by 8, then I actually end up getting a whole number. Okay, but most of the time you won't be getting a whole number, you'll be getting a real number. Okay, something with a point something something. It's just weird that this number perfectly gives you 8 if you multiply it by, perfectly gives you 13 if you multiply it by 8. But it's obviously not always going to be like that. So that's why I like showing examples like this, because this is a weird example because you might find it and then you might even doubt, oh, hang on, something's wrong here. But I was expecting a real number. And that's it. So that's how you would basically represent real numbers. So that also then brings up some questions, right? So that's really great, very easy to do. But then how do we represent pi, for instance? Or how do you represent the square root of 2? Okay, and these are like really long numbers, right? I mean, pi goes on for infinity. It's non-recursive and non-terminating. The square root of 2 is the same. It goes on forever. It also doesn't recur. And then we're going to have a discussion about, and it's a discussion that every computer scientist needs to have at some point in their life too. What we're actually doing is we're mapping an unbounded world to a bounded machine. Okay, and I remember in class last time there was a student who asked me a question about, well, why don't we just compress things and make it smaller to store it? Well, you can't compress something like pi, okay? You have to truncate it. You have to cut it off. You have to cut off some of the digits. You got to save what you can and then not save the rest of it. So here with pi, for example, in a 64-bit machine, if I go back, the mantissa allows us to store, and on a 63-bit machine, we can store about 54 digits of pi using one of these representations. So we can store 52 digits of pi. Okay, if you want to segment pi into multiple different real numbers, you can obviously represent more. But bear in mind that space is finite in a computer, and eventually you're going to run out of space, and you're not going to have any more space to do anything. Okay, so we're done talking about numbers, right? There are other discussions that we need to have. Remember, in the beginning of this lecture, right at the beginning, if I go to the top, there were other things that we needed to represent. Okay, so we represented numbers. That's wonderful, but we still have to represent text. Okay, so now let's look at representing text. How does it actually work? Okay, so when representing text, it turns out that we need some kind of, just when we represented numbers, we have to have some kind of consistency when representing it, because if I decide to change computers, then the way I represent text using binary strings should be consistent. And as I said before, we use binary strings to represent everything, right? Those bytes represent video, text, audio, and everything. So we basically need a way of also representing different characters. So, in other words, let me first write the heading. Let's first put your text representation. Okay, this is text representation, and yeah, the main goal is to assign binary codes to text. So that's the big idea. Okay, but then the question is, how many bits do we need to do this? How many bits do we need? Okay, and this is a big question, because we have English and we have Chinese and we have Mandarin. Mandarin is Chinese. We have Russian and Hindi and Arabic, and there's so many different characters. Okay, so just looking at text, right? We have how many letters of the alphabet is there again? Is there 26? 26 English letters, right? So how many strings of zeros and ones, or how many bits do I need to represent the 26 letters of the English alphabet? So it turns out that if you have to, okay, we can actually see. So we're trying to find the smallest number r, which is greater than or equals to 26. This is what we're trying to find out. Okay, so let's see. Okay, well, 2 is not enough, right? With 2, you can only represent 2 things. With 1 but you can represent 2 things, either 0 or 1. Okay, with 2 bits you can represent 4 things. Okay, you can have 0, 1 or 0, 1, so you can represent 2 multiplied by 2, you can represent 4 things. With 3 bits you can represent 8 things. With 4 bits you can represent 16 things. With 5 bits you can represent 32 things. So 5 bits is sufficient. If r is equal to 5, then 2 to the power of 5 is equal to 32, and that number is indeed greater than 26. All right, so 5 bits is enough to get all of the English letters. And it turns out that we have done this, and we did this using something called ASCII. So I'm trying to look for an ASCII table for you. If you just Google the word ASCII table, you'll find something like this. Just give me 1 second. I'm looking for a good example. Okay, so this is what I'm looking at. You'll find ASCII table. Where can I find an ASCII table? Here we go. Yeah, this is a nice one. Here we go. Here's an example of an ASCII table. Okay, if I have to click onto that, it's not going to get me the image, so I'm going to have to do it this way. Okay, so here's the ASCII table. So here we've got a decimal number assigned a hexadecimal number. So the decimal number is just the converted hexadecimal number, and you could have even had the binary number in here and the octal number as well. But the point is that there's 127 things in this ASCII table. And this is the standard English letters, A to Z, capital letters and small letters. And there's also some numbers here as well. There's some there's an exclamation mark, and here is a hash and a what is this thing called? A modulo, a percentage, an ampersand, and so on, right? Less than is equals to, greater than, a question mark. On this side, you've got a an @ symbol, and so on. So all of these are familiar things, but these first 32 is not familiar, right? So the first, and this is like, again, going back to what I was talking about when I said we sometimes, just because of historic reasons, we do things inefficiently. So, for example, you already saw an example before, but here's another example. In the ASCII table, the first 32 characters are useless, because back in the day when we had teletype and teleprinters, we would use those particular as commands, as instructions, to be able to use the device. But we don't do that anymore. And now we have 32 instructions that are useless to us. But we could have replaced them with characters, but we don't, because we want to keep the representation standardized. So that's a good example of it, right? So, but the point of ASCII is that we actually are representing characters using 7 bits. So we can represent 127 different things, 128 actually, 128 different things. 32 of them are unusable. The instructions that we don't use, maybe we use 1 or 2, but we don't use most of them today. And the rest of them are actually printable characters that we can use to write an email or do anything we want to do. Except that we can't do anything we want to do, because if we speak Mandarin or Russian, or if we speak Hindi, we really can't use this ASCII table. Or sure, the numbers there can be used, because we use numbers in these different languages too, but everything else is now completely useless. So if you want to write a message to your friend using the ASCII table and you speak Hindi and he speaks Hindi, then it's not going to work. Okay, so it turns out that there's another kind of table that is also used, and this is called the Unicode table. So let me see, I hope I can actually get a nice example of this. Okay, so Unicode. I'm trying to find one. So obviously it'll be very difficult to find one, because, okay, yes. Okay. Okay, I'm just trying to look for one example. One small example. Okay, here's a small example. Oh, but this is not very clear. Oh, there we go. Okay, so here's an example of a Unicode table. So do you see here we have a much richer description of characters that we can use inside of our email now. If you're going to send an email message to your friend, this has a much greater variety of words, of letters to use, and we can use these letters to basically make messages in different languages and so on. So each of these letters are assigned a particular binary string using n bits, and you can do a lot of interesting things with it. So in an exam, I will give you the ASCII table inside of the question if I ask you to write a particular word in ASCII. Right, let's look at an example of when there is a text-based storage and transmission, right? So for example, in emails, we have protocols which allow reliable transmission of text. Okay, so we can use something called a base 64 encoding to encode binary strings into text. And the reason why I'm showing you this is I can show you how ASCII can be used to encode binary information. Okay, so let me just write this down a bit better. Okay, so when there is text-based storage and transmission, for example, in emails, Okay, we use base 64, so base 64 encoding. Okay, so then what is this base 64 encoding? Okay, so just to say this in a different way, base 64 encoding is used to carry binary data across channels that only support text content. Okay, so let's actually then define what base 64 is. Okay, so what is base 64? So the base 64 encoding divides the binary data into 6-bit groups. Each 6-bit group is then mapped to one of the 64 ASCII characters forming the base 64 encoded output. Okay, let me just read this to make sure it makes sense. Base 64 encoding divides the binary data into 6-bit groups. That's correct. Okay, each 6-bit group is then mapped to one of the 64 ASCII characters. Okay, forming the base 64 encoded output. Okay, so that's really great. So then, yeah, should I draw the base 64 table? Okay, I think I should. Or better yet, can I just find the base 64 table for you? Okay, so I found this one on Wikipedia Commons, and this is an example of the base 64 index table. Yeah, so looking at it, can you see that the decimal value 0 is assigned to A, the decimal value 1 is assigned to B, and 2 is assigned to C, and so on. And there are 64 different things here to look at. So from 0 to 63. And yeah, so you've got all of the capital A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, and then you got the A, B, C in small, starting from 26 all the way to a small z at 51. Then you got the number system that starts from 0 to the base 10 number system from 0 to 9, and then 62 and 63 is a plus and a dash. Okay, all right. Okay, good. So that's what we have so far. Okay, so remember that, because, well, you don't have to remember that. I'm obviously the ASCII table, the Unicode table, the base 64 character table. I will give you those things, so you don't ever have to remember them. But you should know how to use them, because obviously now we're using it, and you need to know how to use it. Okay, good. So looking at so you now know what the table looks like. Okay, so now let's write out the algorithm for encoding. So the algorithm for encoding. Okay, so first, the binary data is segmented into groups of 6 bits. Okay, so when I say binary data, I mean when the characters that you want is converted into the ASCII binary digit that corresponds to that character. Okay, and I'll show you an example now, but that's what I mean by binary data. Okay, if the total number of bits is not a multiple of 6. The data is padded with extra bits. Okay, these are usually 0. So in this course, we will use zeros for this to make up the difference. I hope your notes looks better than mine. I think on Monday, when I come back, you need to show me how you wrote this better than me, okay? So this padding is later indicated in the encoded data by the equals to symbol. Okay, so this is the algorithm, all right, and I'm going to now show you how to do this by means of an example. So let's now get a new page and write your example. So the example here is, let's encode the word hello using base 64. Okay, so that's the question. So the word hello, if you look up the words hello in the ASCII table that I showed you before, you'll find out that H is actually 72 in base 10, right? E is 101 in base 10. L, small l, is 108 in base 10. And there's two L's, so you have two 108s in base 10. And then you have 111 in base 10. Okay, so you look up that in the ASCII table. Then you convert these numbers into binary. You can use PNP to do this. So it becomes then 0100100. Okay, that's the number in base 2. 011000101 in base 2. 011011100 in base 2, and that's repeated again, so 011011100 in base 2, and then finally, I hope it fits, it's going to be 011012334 in base 2. So this is now the number in base 2. So then the next part of the algorithm is to next, remember what we said in the algorithm when you wrote it down, we have to regroup this. Regroup the binary sequence into 6-bit groups. Okay, instead of 8-bit groups. Okay, can you see there's 8-bit groups right now? So we need 6-bit groups. Okay, and then we have to also pad as necessary. So this now becomes is equals to 0101010. So, all right, 000110. All right, so in other words, you see this part here, 1 2 3 4 5 6. That part there is this part here. Okay, and then let's change the color. 1 2 3 4 5 6. That part there is this part here. Okay. Alright, so then what's the next one? It's going to be 010101. Okay, I'm just copying from the top there. 101100. It's okay. 011011. And then 000110. And then finally 1 2 3 4 0 0. Okay, so just copying it from the top. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. I see what I do. I have to cross check all the time to make sure I didn't make a mistake. Right, so now this is really wonderful, right? So far so good. So what did I do here at the end here? Did you notice here that there were 4 ones here, and then now there were 4 ones here? Why did I do this? Why did I add those 2 zeros there? Remember that in the algorithm I wrote for you, I wrote there that if there isn't, if the output isn't a multiple of 6, I need to add zeros to make it a multiple of 6. So here it wasn't a multiple of 6 because there were 4 characters at the end, and I needed to add the other 2 characters to make it a multiple of 6. But I need to remember that I added 2 zeros, because if I add 2 zeros, it becomes 1 equals to sign. If I add 4 zeros, it becomes 2 equals to signs. If I add 6 zeros, it becomes 3 equals to sign. So any 2 zeros become 1 equals to sign. Okay, 4 zeros becomes 2 equals to signs. Okay, so you can remember that. You have to remember that for when it appears now, right? Right, so that's really great. So far, so good. Let's now actually look at the actual conversion now. So we're going to change our colors to red and then convert it. So this here, if I go to my base 64 table, okay, so let me write down the next instruction. So next, we use the base 64 character table to map each 6-bit group into a 64-bit character as follows. Okay, I'm going to say as follows, right? But I'm actually just going to do it here at the top. Or maybe is there a way to cut and paste here? Okay, I don't think so. All right, it's okay, I'll rewrite it. It's not a problem. I mean, you're going to rewrite it, so it makes sense that I also rewrite it. Okay, so that becomes, oh, you know, I'll do it in a different way. I'll do it as a table. So it becomes 0, 1, 0, 0, 1, 0, right? This number, this is the first one. This becomes 18 in base 10, and on the table it becomes an S. Okay, on the base 64 table you find this 18 is an S. Okay, and then this is 0, 0, 0, 1, 1, 0. It's a number in base 2. This number is base 6. Sorry, is a 6 in base 10, and becomes a G. Then you have 0, 1, 0, 1, 0, 1 in base 2. It becomes a 21 in base 10, which is a phi. And then you have 1, 0, 1, 1, 0, 0, 2, which is 44 base 10, which is an S. Am I right? Yes, I am. Okay, good. And then this next one is, notice this is a small s. Okay. This is 0, 1, 1, 0, 1, 1, which becomes 27, which is equal to a small b. Okay. 0, 0, 0, 1, 1, 0 becomes 32, which is big G. And then 1, 2, 3, 4, 0, 0 in base 2, which becomes 60, 10, and that's an 8. Okay, so far so good, easy, right? Remember that I added in these 2 zeros here, okay? So then since we added 2 to the last group, we, well, this should be a comma, we add 1 equals to sign. We should add 1 equals to sign at the end of encoded string. Okay, therefore, hello becomes, when you convert it to base 64, it becomes S, G, V, small s, small b, capital G, big, oh well, 8 is a 8, and then the equals to sign. Okay, that's how you do it. Okay, right, simple enough. So to reverse the process, well, you just have to reverse the process, right? So if I give you this here, how do you go backwards? Okay, how do you go backwards? Well, it's not that difficult, right? So I'll leave you to do that as an exercise, but I'll give you the overall algorithm. So for each of these S, capital S, big G, big V, you got to convert those into a 6-bit string. Okay, just as you did here. So for each of those, we'll have to get these. So in other words, you're going this way now, right? So I'm going to change the color of my pen just to help you kind of picture what's going on here. So this, you're going to have to go this way. Okay, so you're starting off with S to decode it, then you convert it backwards. Okay, G, you convert it backwards. V, you convert it backwards. Okay, then you put them all together. You put them all together like this. Okay. And then you realize that, hang on, this, my input, what I'm trying to decode, had an equals to sign at the end, which means that I added 2 zeros inside of it. Which means that when I come back to this step, I need to remove those 2 zeros. And then I just then regroup it according to 8s to get me this. And I'm done. Because then from the 8s I can get my 10s, and from the 10s I can get my binary string. I mean my input string. So you see the process is completely reversible. Okay, just reverse it. Right, so that's the end of text. So now you know enough about text to be able to, so you know how text is represented and how text can be used to even encode information in binary. All right, so as promised, we also need to look at audio. So let's now go to audio representation. Oops. Okay, so in audio representation, we are really interested in modeling. Hear that sound? I don't know if there's a sound by you, but I can hear my 2-year-old making a noise in the kitchen. I can hear some beautiful music as well, but I don't know where that's coming from. But yeah, there's lots of sounds around me, and I'm sure there's a lot of sounds around you. So that's very fascinating, right? I mean, how exactly, how on earth do we even perceive that sound? It's so amazing that our brains can interpret vibrations in the air. So so we actually want to be able to represent those sounds inside of a computing system, because it's one of the things that humans really like. And not well. We also want to represent what is actually hearable to a human, right, and not necessarily what's hearable to any other species like a dog, or we might not necessarily be interested in that. So in order to, so we'll talk more about what is relevant in the next lecture in terms of relevance in what to store. Like I said, we might not be interested in what a dog wants to hear, but we'll talk about the relevance of what's important to actually store in the next lecture. But right now, I'm going to focus on data representation. So sound, as you know, is it comes as an analog signal, right? It travels through the air as a physical object, as a physical thing. So this is an example of a sound. Can you see it has an amplitude? So we describe something like this as analog. So let me write it down here. So this is analog. So analog is smooth. It varies. It's continuous. So an example of analog signals is sound and also temperature. Okay, so temperature is also an example of an analog signal. And this is contrasted to digital. And digital is discrete. It has few values. also a finite set of values. These values are isolated points of measurement. Okay, so examples of this can be, I don't know, oh, what about Morse code? Okay, so Morse code is an example. Okay, but what we want to do with the physical sound, which comes to us as this beautiful curve, is to basically digify it. Or we call actually say digitize it. Okay, digify. And to digitize it, we have to somehow take it from this continuous space to a discrete space. So we are really interested in converting this analog signal into a digital form, because remember, in memory, each of the different intensities of the signal needs to be saved as a binary string. So we can represent each of the intensities as a number, and the number can be represented as a binary string. So if we, for example, represent this part of the signal as the number 3, then that 3 can be stored as the number 00000011 as a binary string. Okay. If there's negative numbers even here, we can actually also represent that as using binary strings, using 2's complement or whatever. But the point is that there is a way of capturing just a point of this curve. We might miss a few, right? I mean, we are losing information when we miss it. But we sample we call this sampling. We sample the signal at at fixed intervals. It's called fixed intervals. Okay, these are fixed intervals, right? Intervals with R. Okay, so we sample the continuous analog signal in fixed intervals. Okay, so there's an algorithm that actually needs, so we need to learn in order to do this, and this algorithm is called, it's called the sampling and quantization algorithm. Okay, and it's a very simple algorithm. So the first part is sampling. So when we hear a beautiful sound outside, we need to take measurements of that sound. Okay, at fixed intervals. Okay, and we often take these measurements according to something called a sampling rate. And this is basically how long we wait before we take the next measurement. That's our sampling rate. And the second part of this algorithm is called the quantization part. Okay, so you could spell it with a Z or a S. I mean, it doesn't really matter. Quantization. And here we map each sampled value of the signal to a discrete level. And we call this discrete level the quantization level. Okay. All right, so this is the algorithm. It's a very simple algorithm. So there's actually a lot more to say about this, but I'm not gonna focus on that. So there was actually, I was meant to actually emphasize something called the Nyquist-Shannon theorem, and there was other things also about sampling rates and how to basically find a suitable sampling rate with based on this Nyquist theorem. But I've removed it just for the sake of there's other things I wanted to add to. So if you are interested in learning about those things, then just go ahead and Google them, and you'll find out that there's actually a very beautiful theorem called the Nyquist-Shannon theorem, and it says that if you want to know how to perfectly reconstruct a signal, then you basically have to sample 2 times the highest frequency of that signal, right? So it's actually it's not so difficult to understand. Maybe it does require some explanation, but I'm sure you'll get it on your own if you can go and Google it. I'm not saying that it's examinable at all, right? So the Nyquist-Shannon theorem is not examinable. It's very much for your own interest. Okay, maybe I should write down the name of the theorem here. So it's the Nyquist. Nyquist-Shannon theorem. Okay. Yeah. Okay. All right. So that can be for you to just Google out of interest, but not examinable. Right. Okay. Right. So what are we going to talk about then? Right. So that's basically it for sound, and in the so this is basically what we do, right? So we basically have a physical phenomenon of sound which we record based on the intensities of that wave that reaches our senses. We record those signals in using a fixed intervals, and according to some particular sampling rate. The Nyquist-Shannon theorem tells us how much of samples we need to take in order to perfectly reconstruct the signal, and it's always 2 times the amplitude of the signal. But these are all for interest. And that's it for sound representation. Okay, so yeah, the problem with this course is that there's so much to talk about and there's so little time. But my job is to really just introduce you to the different points of interest, and then you can go about actually learning more about each of these things. Okay, so the second last thing that we need to talk about is how do we represent images, right? So right, so yeah, so this is an interesting concept, and it leads to a whole field called computer vision, image processing. But here we're just going to discuss the very basics of image representation and vector representation. Okay, so when you imagine how do I put this? So when you look out at, let's say you at the Hartebeespoort Dam, and you're looking out and you see something quite beautiful. You see the dam, and you see the green trees, and the beautiful mountains. All right, and this is not too far away, right? I think it's an hour's drive north. Not really north. Is it north? It's northwest. Well, somewhere on that side. And you see all of these beautiful things, right? So there's blue skies. You've got some beautiful trees. Okay, I clearly don't know how to draw trees, right? I'm just gonna draw something really weird. And then there's a beautiful dam here. Okay, this is water, so okay. What else is there at Hartebeespoort? There's some mountains. They're not very big mountains, but there are some kind of mountains there. Okay, so you're standing here and you're looking at this, right? And you wonder, how can I represent all of this beauty inside of a computer? So well, this can be done in 2 different ways. Okay, so there's the notion of a raster graphic and a vector graphic. Okay, so let's first discuss a raster graphic. The one way we could do this is we could have a grid. Okay, and this grid is a square or rectangle. Okay, and I've got like a little different color pen to show you something else. So if I draw lines going this way, okay, I'm separating the grid into different rows. Oh, sorry, I'm separating the picture into different rows, and now I'm completing the grid by separating the picture into different columns. So these are very broad lines that I'm drawing. Okay, so in other words, the space here between these 2 lines are quite big, right? But you can do this really, really close to each other, right? So you can make this line as close as possible. And if you do that, then let me complete this. If you do that, then we get what is known as pixels. Okay, so this particular box here, okay, but we try to make it as small as possible to describe that segment of the image. This is an example of a pixel. So pixels are quite intriguing in that individually they are all the same color, but when they put together, they make up beautiful images. And so we sometimes have to change the representation of the pixel to represent different kinds of images. So for example, for a black and white image, the pixel here will just represent a intensity, let's say from 0 to 255 of different shades of gray, right? So we'll start off with 0, which is no intensity, okay, so that's black, and then we'll go all the way to 255, which is white. So everything between here are the different shades of gray. So maybe the number 25 is more close to black than it is to white, whereas 200 is more close to white than it is to black. And so we'll get a different shades of gray for each of these different pixels. Our alternate representation for the pixel has something called color depth. And here we refer to this as a 24-bit color depth, which means that essentially we get 3 pixels for each color. Oh, sorry, we get 3 bytes for each color. Not 3 pixels. You get 3 bytes for each color. So in other words, 1 byte is going to describe a particular color. Okay, so that's 1, 2, 3, 4, 5, 6, 7. Okay, so that's 1 byte. Another byte is going to represent another color. Another byte will represent a different color. So this is 24 in total. So 8 plus 8 plus 8. That's why it's called 24-bit color. Okay, so right. So this is, for example, if we have this number here, it describes a number between 0 and 255, and that color represents that particular color is an intensity of this color represented by this particular byte. So how do we then decide what colors are we going to be using here? So it turns out that that's a discussion about different color models. So the color model that we use here is the red color, R, G for this one over here, and B. So red, green, and blue. So we have the red color, we have green, and we have blue. All right. And by mixing these colors together with different intensities, we achieve different types of color, which is quite remarkable. It's quite amazing. So we'll get more into this in a few minutes, but for now what I'm describing here is a raster graphic. Okay, a raster image. Let's just say a raster image. Okay. Yeah, so that's how raster images work. It's a whole lot of pixels put together in a certain grid, and each of the pixels correspond to either a single palette of a single byte, which describes the 0 being black and 255 being white, and it gets all of the different shades of gray, and we refer to those as grayscale images. Or on the other hand, we can arrange these pixels as a 24-bit color depth, in which case we have 3 different bytes that correspond each to a single color, and these are often the primary colors, so that we can mix them up to achieve any other color that's possible. Right, so that's the big idea. So these are the ones that are possible for human perception. All right, that's a pretty important point, because we're trying to model human perception here. Okay, yeah, so that's what raster graphics are. On the other hand, we can actually represent, oh, I can leave that there. On the other hand, we can represent an image in a different way, and that way is called using vector graphics. Okay, so this doesn't use a grid. Here we use mathematical equations to describe the thing that we're looking at. So for example, if I draw a heart like this, okay, this heart isn't very good. Right, let me see if I can get the next part right. Okay, so that's a heart, okay? I can describe this heart using mathematical symbols. So this can be 16 sine to the power of 3t. Okay, that's the one part of the heart. And then the other part of the heart is y 13 cos t minus 5 cos 2t, okay, minus 2 cos 3t minus cos 4t. So you've seen these things before, but we can't really in our minds render what this image will look like by just looking at these equations, right? We'll need a computer to actually substitute values of t so that we can reconstruct the heart to look like that. So that's quite interesting, right? So what is the difference between raster graphics and vector graphics? So from the descriptions that I've given you now, let's talk about the different aspects of them. So the different aspects of raster graphics. So I think the best way to do this is in a table, right? So we'll talk about raster graphics, and we'll talk about vector graphics. Or images, right? It's you can use them interchangeably. In practice, they're not really used interchangeably. We usually refer to raster images and vector graphics, but I mean, that doesn't really matter. That's a small detail. That's not important. So file sizes. As far as file sizes go, which of these take more size? Is it easier to store this equation in bytes in memory, or is it easier to store 3 bytes per pixel in memory? So 3 bytes per pixels in memory is what we would necessarily do for color imaging with raster graphics. So we can expect this to be larger, because here we're just storing a bunch of equations, a bunch of numbers, a bunch of representations for these equations. So this is much larger, and it depends on something called resolution and color depth. So you already know what color depth is. But what is resolution? Well, on the previous slide, I did implicitly talk about resolution. The resolution is the number of total pixels that you have. So what you often do to get the resolution is that you take the number of pixels that are going this way. So here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for this particular example. So that'll be 12, and then you multiply it by well, not the height, but the length, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 9. So that's going to be 2 by 9 is the resolution of this particular image. All right. So that's what we would generally do. All right. So so that means that vector graphics are much smaller because they don't have this resolution. Because remember, for the resolution, to work out how much of bytes you would need, depending on whether it's a black and white image or a color image, you would need to times the number, the color depth, which can either be 1 byte for a grayscale image or 3 bytes for per pixel for a color image. Multiply that by the resolution to get the number of bytes that you would need for the image to occupy. And we're not even talking about any other auxiliary storage that's required. So this is much smaller, and it depends on the complexity of the shapes. Okay, so just for this heart, we would require these 2 equations. But if you're going to have more shapes here, like maybe you've got like a circle coming out of that and an arrow coming out of this or whatever, then you'll require more equations, and that increases the complexity of it. But I mean, equations are not really that much of space to store. So generally, vector graphics are much smaller, even with very complex shapes. Yeah. Okay, so let's talk about scalability. So when we talk about scalability, we talk about if I have to take this raster graphic and make it bigger, is it scalable in the sense that I can change the size of it? So if it's a small, if it's a very small one, like before we had, I think, what is it, 19 by 9 or something? Let me go back and see what I wrote here. This was 12 by 9. If I have to go and try to make this image bigger, blow it up, right? Then how much of work is that actually going to be, and do I actually get any do I actually get anything out of it? So it turns out that with raster images, when you scale it up, when you try to zoom into it, you lose the quality, right? So there's a loss of quality when scaling, and this needs higher resolution, which means really that in order to make a raster image better, you need to be able to fill those pixels meaningfully so that it can scale better. And the best way to do that is to have a very high resolution so that if you scale it up, then you can still make out what's going on in the image. Whereas if you try to scale that small image that we had on the previous slide, part of the notes, then you really have no luck with that because the resolution is very small. So I'm sure you've heard of HD and 4K. 4K is about it's a hell of a lot more than HD, which means that you can blow up the image on a very big TV screen and you'll still be able to make out what's going on. In terms of scalability for vector images, it turns out that even though it's more difficult to actually create the shapes and the equations and all of that, it turns out that it's easily scalable and you can zoom in infinitely. Okay, and that's really what makes this vector graphics amazing and appropriate for icons and stuff like that, because you can actually scale it up, or what is it, logos for companies, so you can scale it up for advertising and you'll never ever lose quality. But I'm sure you're wondering, well, why is it that you can do this infinitely? You can infinitely zoom into this heart. Because it's a mathematical equation, and mathematics, this nature is closed. I don't know if you remember when we spoke about closure, associativity, distributivity. It's one of the axioms that I can actually multiply this by any real number, and I'll get another number within the same domain. So if I say x multiplied by this particular number, if I multiply, say, let x is b equal to 3, then I can get it'll be 3 times what it was before. So I can multiply that by 3 and multiply this by 3 too, and I will get a real number. So it is very possible to multiply it by any integer or real number r. Okay, so that's pretty amazing. So you can scale it infinitely. But theoretically, you can scale it infinitely. So when do we use these things? So the preferred use of these images, it really depends on what you want to do. So I'm sure you noticed that with raster images, because even though it takes a lot more space, if you can have very detailed images, and for detailed images, we often want that when we want to take photographs, right? So, for example, we can take a picture of our face and we can see there's a pimple on our face, and it'll come out very clear in one of the pixels. So the photographs is a very convenient way to do that. If you want to go on holiday and take a picture of the mountains and the trees and all of that, you can just take a snapshot of it and it stores it as a raster graphic, and you didn't have to make up your mathematical equations to find out what you were actually looking at, or to render it. So so in that case, vector graphics is really much more suited for logos and icons. Okay, all right, so now let's talk about editing. So editing raster images and editing vector images. Well, let's look at editing raster images involves, well, pixel-based editing. Okay, so when doing pixel-based editing, you have to basically change each individual pixel. And if you have, let's say, 720 by 1080p displays, so something like this, for you to make just a small change somewhere in the graphic, you would need to individually change every single one of these pixels in order to do it. And you got to have smooth transitions. Okay, now we've got AI algorithms that can do this with ease, right? But depending on what you want to do, it might be an extremely difficult task. So this pixel-based editing is quite problematic. But there has been some advances in artificial intelligence which helps us do this. Okay, so it's a challenge to make large scale changes. All right, and then, well, vector graphics are extremely easy to edit. You just simply change the equations. Okay, and basically the changes are made without influencing quality, which is a big thing too. So that's very easy to change. The next thing we need to look at is the examples of the formats, and this is something that we're not going to take a lot of time to talk about. So here we can have so examples of formats. Examples of formats is JPEG, Joint Photographers Expert Groups. Then you have PNG, Portable Network Graphics, and BMP. And then examples of vector graphics. So you might be thinking, I'm never going to use vector graphics. You might be thinking that. But in actual fact, in computer science, we require you to use something called LaTeX to do all of your documents. So you might have been used to Microsoft Word, but in your degree, your lecturers will teach you how to use something called LaTeX. And in LaTeX, you can actually render vector graphics. And you'll find out that it's sometimes a pain to do it, but it's very much worthwhile because you have the quality in your work so that your work, wherever it is published, the images are always crisp and clear. So you will be using these ideas, so don't just think that you're going to forget about vector graphics. In fact, you might turn out to love vector graphics and use it for almost everything in your research and assignments. Whereas these raster images, there's issues with that as well. Okay, good. So I'm very happy about that. I think that you probably understood what was going on there. When we talk about images, though, we must also talk about something else. So we must talk about a color model. And there's two color models I'm going to teach you. I'm going to teach you about RGB. This is the RGB color model. Oh, I shouldn't have made that. Okay, there we go. So the first one is the RGB color model, and this is mainly used for color displays. So color displays are things like scanners, monitors, cameras, etc. Right? So now your monitor on your screen, for example, is a good example of a display. So here we use a light intensity, so it has to do with light. Okay, so and when we talk about the RGB color model, we have to talk about the primary colors associated with it, and it's actually in the name. So it has to do with red, green, and blue. So I'm going to draw the color triangle to help you picture what's going on here, right? So, all right, red. Okay, and then you've got yellow, magenta, and cyan. So if you've never seen magenta and cyan before, then it might be a good idea to Google it. And so this is called magenta. This is yellow. This is cyan. This is red, blue, and green. Okay, let me see if I can find the magenta. Oh, here we go. So cyan looks like this. Cyan looks like this. Okay, it looks something like this. Okay, magenta is it's like a purple kind of thing, like this. Okay, do you know what red is? That's red. This is yellow. Okay, this is blue. Oh, okay. So that cyan and blue are very similar. So I don't really have a blue to show you. And green, green. This is green. Let me see if I can get a nice blue color palette. Okay. Looks like I'm not able to actually. Oh, there we go. That's blue. Okay. Oh, damn. Okay. Okay, blue didn't come out the way I wanted it to come out. But yeah, okay. I don't know. I couldn't find a nice blue for you. Okay, so this is the blue if you can see it on your screen. But you know what blue is, so I'm just gonna go. I'm just gonna, yeah, exit stage left. All right. So what this triangle? You have to remember this triangle, right? So I don't know how you're gonna remember it. I can tell you how I remember it. So I remember it as um, Russian girls are beautiful, yet make me crazy. Okay, so you think of something smarter than that. Although I think it's because it's so ridiculous that I remember it. All right, but you can remember your own way of doing it. Some students used to tell me YMCA or see this YMC. So you know that song YMCA. Then you can make up another name for the rest of it. But RGB is already a clue that you have R, G, and B. Okay, but anyways, once you remember this, then you can start deducing the different colors associated with it. So, for example, if I go to, if I say, what color is rendered in RGB when you have this particular vector, okay? So this is an example. So what color is rendered in RGB if you have this vector? So then you're going to say, okay, great. So this is R, this is G, this is B. Okay, so then it's green. So this is green. Okay, so the answer is green. Then I ask you, well, what color is rendered if I give you this particular vector? So, well, then you're going to say, well, this is R, G, B, right? So then this is a mix of full bright intensities of R and red and green. So if you mix red and green together with full intensity, 255 of green and 255 of red, you get yellow. So the answer is yellow. Okay, similarly, you can have something like this, 0, 255, 255. Or you can have this, 255, 0, 255, and so on. You can just decide what these different things are. Okay, so so that's how you do, that's how the RGB color model works. Let's look at the other color model. Let's look at the other one I want to show you, which works on subtractive color theory. So this one here, the RGB worked on additive. Okay, so we were adding colors together. Like here, we add these two to get a new color. Okay, so this next one is based on subtractive color theory, and it's called the cyan, magenta, yellow, and key. So also called CMYK. Okay, so this is CMYK, cyan, magenta, yellow, and key, and it works on subtractive color theory. And subtractive color theory, well, it has to do with subtraction. So I'm not really going to get too much into detail with this, but it works under the same principle, right? So here you're giving percentages of different colors in a vector, and you got to decide what kind of color it is. So for example, here this is key, so this is black. So theoretically, if we mix equal intensity of cyan, magenta, and yellow, we should get different shades of black. But in reality, what we end up getting is some kind of muddy brown, okay? So that's why we introduce a new, and that's because of physics, and it has to do with some physical properties of the mediums and so on, but it's out of the scope of this course. So what we actually do is then we have a separate toner for key. And this is often used for color printing, this model, right? Because it subtracts the intensity on the color, right? Subtracts the intensity to determine what's the next color to put onto it to get a different type of color. Okay, so this is color OUR. This is color printing. So your printer at home, for example, uses this. So anything where you have to print something using color on a piece of paper or on some kind of medium, you're probably using subtractive color theory, whereas additive color theory is used on screens, monitors with light intensity. And here it has to do with subtracting the colors. Right, so let's do an example. So if I give you, also notice one more thing, that these primary colors for the RGB was red, green, and blue. But the primary colors for subtractive color theory is different. It's cyan, magenta, and yellow. Those are the different primary colors for the subtractive color theory. Right? It's very important to remember that, because I'm probably going to ask you that question in the exam. Right, so let's look at an example. If I say, what color is this? So 100% of this, 0% of that, 100% of this, and 0% of that. So here we have, you're going to use cyan, magenta, yellow, and key. So this cyan and yellow is 100%. Well, it turns out you can use my triangle, my saucy triangle, to figure out what the color is. So cyan C is over here. I'll use a different color. Let me use a red, right? Okay, so this cyan here, right? That's this here. And then the yellow is here, okay? That's this here. And together, these two things, when put together, give you green. Okay, so this is going to give you green. The secondary color is green, okay? So I know I'm only showing examples of these 1, 2, 3, 4, 5, 6 different colors, but in reality, you can get any colors you want. Okay, so we're almost at the end of this lecture. I know it's been a long one, but we're almost at the end. The last thing that we need to talk about in this lecture, the last thing about data representation, has to do with videos. So video representation. So video representation is always a very intriguing concept. So what is a video? Well, you probably already know what it is. So we display rapid sequences of static images and we also call images frames when we talk about a video representation. So we refer to images and frames. They're both the same thing. Okay, so in your mind now, picture a flip book or some kind of notepad or something where you've written some stuff down and you flip through it rapidly. So in the first frame, you see a man, and then the man, if you measure from year to year, it's some maybe K, right? But then the man moves a little bit more on this side, on this frame. So this is now K plus 1. Okay, and the man moved a bit more on this frame. This is now, oh, I threw that thing in the wrong place. Is that an eraser? Yeah, that's an eraser. Okay. So this is K plus 2. And then you a little bit more. Maybe he's standing there at K plus 2 now. So he's not moving. And then he moves back again. K plus 1. Okay, so yeah, in these frames, the man started off at K, and then when we looked at the next frame, the man moved a bit more that way, and then the man moved a bit more that way, and then if we just go past these images very quickly, we can see that the man is going back and forth. And that's basically how we do video. So the more of these frames that you have, the more frames you have, the clearer the picture. The clearer the picture of the video. And that's really great because, you know, you want to be able to have as much clarity as possible. But the big but is that we have now a trade-off between file size versus video quality, right, which is a pretty big deal. The file sizes means that it means how many of these frames are there actually, because remember, for every frame you've got to store the resolution multiplied by the color depth, right? So for example here, if this is your N and this is your M, then you've got to store N multiplied by M times 24-bit color, the 24-bit color depth, okay? And that's a lot of memory, right? And this is times the number of frames that you've got. So if you've got like about if you got X frames, then it's X multiplied by N multiplied by M multiplied by 24 bits, which gives you 3 bytes, right? So that's actually a pretty big deal, and it blows up, right? So file sizes is a big thing to worry about, and obviously trading off the file size trades off the video quality, because the less frames you have, sure, the file size decreases, but it also means that the video quality decreases as well. So a good compromise is for to look at the frame rate, which is the number of frames per second. Okay, for movies, it's usually for the movies like Transformers or any kinds of movies. I don't know why Transformers was the one that popped into my head, like Lord of the Rings. Okay, something more elegant. I don't know any other good. How about Amadeus? That was a good movie. So for movies, there's 24 frames per second. Okay, and on something like YouTube, where the videos are much shorter, so this is very long videos. Okay, in YouTube, where the videos are much shorter, all right, we usually have 24 to 60 frames per second. So it can be anything from 24 to 60 frames per second. Yeah, so that's basically it from the data representation part of things. And that's all of the things you need to know about data representation. In the next lecture, we will look at data management and security. So what do we mean by data management and security? This is number 3. This is the third lecture. And so data representation is really about getting these different multimedia into the bytes, right? Into the different bytes. So that's basically what we spoke about now for I don't know how many hours, maybe 2 hours, 2.5 or something like that. But when we talk about data management and security, there we're really interested in, now that we've got all of the stuff inside of these bytes, we've got all of the data as zeros and ones inside of these bytes, then how do we actually manage that data? How do we compress it? How do we make it smaller? How do we make it fit into smaller mediums? How do we secure it to make sure that people can't just interfere with our data? So that's what we will study next.